Hello everyone, and welcome back to another calculus video. In this video, we are going to talk about how to integrate improper integrals. And by improper integrals, I mean we're integrating with this idea of going to infinity or negative infinity. And we're going to have to rewrite these in terms of limits. So the idea of L'Hopital's is going to come back for us too when we evaluate. So let's say we have a function that's continuous on the interval from a to infinity. So we would write the integral this way, but to evaluate, we're going to replace that infinity with the letter, and we could use any letter, they're just using b here. And then we would integrate, and then we would take the limit as b goes to infinity. Likewise, if we're looking at a continuous function on the interval from negative infinity to b, and we want to evaluate, we would rewrite that lower bound as a variable, integrate, and then evaluate the limit as, and they're using the variable a as a goes to negative infinity. If we want to evaluate from negative infinity to infinity, then we could split that up as going from negative infinity to some value, finite value within there. And we could pick anything. Zero is a common one to pick because it's easy to evaluate usually. So we could go from negative infinity maybe to a number here like zero, and then go from zero to infinity, and then we would rewrite each of these in terms of that limit process. And what we're trying to do is determine, does that integral converge or diverge? Is going to converge when that limit, once we evaluate, goes to a specific number. If it just heads off to infinity or negative infinity, then we're going to talk about something that diverges. So let's look at a few examples. Let's say we want to integrate the function dx over x from 1 to infinity. So we're going to rewrite this using limit notation. So we're going to say we're going to take the limit as b goes to infinity, and I'm going to rewrite this from 1 to b. And this is the dx over x, or we could think about it as 1 over x dx. And when I integrate that, we know that's our ln rule. So this is the ln of absolute value of x, going from 1 to b. And now we would plug in those limits. Fundamental theorem of calculus says this is the ln of b minus the ln of 1. We know the ln of 1 is 0. So we want to evaluate the limit as b goes to infinity of the ln of b. And as b gets bigger and bigger and bigger, that ln is getting larger and larger. So this is heading to infinity, which is going to diverge. Now, let's change the scenario a little bit. What if we were looking at integrating from 1 to infinity of 1 over x squared dx? Or we're going to rewrite that using the limit process. 1 over x squared is the same thing as x to the negative 2. So to integrate, we're going to add 1 to the exponent, divide by the new exponent. So there's my integration, and then we got to evaluate. So now we have negative 1 over x, and we want to evaluate from 1 to b. So if we plug in the b minus, plug in the 1, so this is going to be negative 1 over b plus 1. And we want to know what happens as b gets larger and larger and larger. So as b gets larger and larger, that denominator is shrinking, which means that that denominator is getting larger, which means the fraction is shrinking. So you can see how this is heading towards 1. So this is a different scenario than the one above, all because that exponent was different. So we would say this integral converges. Let's look at another. Let's say we want to look at e to the negative x. So we're going to rewrite this. This is the limit as b goes to 0. B goes to infinity of the integral of 0 to b of e to the negative x dx. And we're going to integrate that. So to integrate, we're thinking about using chain rule. U is negative x, du is negative 1 dx. If we put a negative there, we would compensate here. So when we integrate e to the u, we're going to get e to the u. I don't know what happened to my negative there. Let's try that again. When we integrate e to the u, we're going to have e to the u, and u is negative x. Remember that negative came from when we had our du here, going from 0 to b. And we're going to have limit as b goes to infinity of negative e to the negative b minus negative e to the 0. So let's think about what's happening in this case. This is negative 1 over e to the b plus e to the 0, which is 1. And again, as b gets larger and larger, that denominator is getting larger and larger. So this fraction is shrinking. So this guy is heading to 0. And then the limit as b goes to infinity of 1 is just 1. So this one is going to converge and it's going to head to 1. If we look at that second one, I'm going to draw a little squiggle here. I'm going to rewrite it. 0 to infinity, 1 over x squared plus 1 dx. And this is where you may want to pause the video, try it, and then come back and check your answer. So we're going to take the limit as b goes to infinity. So we're going to have 0 to b, 1 over x squared plus 1 dx. We know that guy is actually arctan. We need to evaluate from 0 to b. I'm going to plug in my limits. Arctan of b minus arctan of 0. Now we know arctan of 0 is 0. The question becomes, what is arctan of b as b goes to infinity? This is where it's going to help to look at the graph of arctan. Our arctan function, if you remember back to trig, looks something like this and is bounded between these asymptotes. This is the line y equals pi over 2, and this is the line y equals negative pi over 2. And the reason we've got horizontal asymptotes here, if you remember, we had to bound the tangent function so it would have an inverse function. And tangent, we looked at it from the cycle from negative pi over 2 to pi over 2. So if I look at the limit as b goes to infinity, so as b gets larger and larger and larger, this is going to head towards that horizontal asymptote of pi over 2. So we're going to take that limit. We've already used it. It's gone. And then the arctan of 0 is 0. So we're going to get pi over 2 for that one. So let's make it a little bit more interesting. We're going to look at this guy. I am going to rewrite this. This is 1 to infinity, and if I distribute, I would have 1 minus x e to the negative x dx. And we're going to think about integrating each of those pieces separately. Oops. When I distribute. This is e to the negative x. Sorry about that. So this guy is easy to integrate. So we're going to think about splitting this up. This would be e to the negative x dx minus x e to the negative x dx. And then we're taking the limit as b goes to infinity for both of these. So I'm just going to try to write this all in one piece here. Let me see if I can clean up my notation just a little bit. There we go. So I have to integrate this piece, then I'm going to have to integrate this piece. This piece is going to be easy. It's just a u substitution. U is negative x, d1 is a negative 1 dx. I would need a negative here and a negative here. That guy's going to require by parts. So I'm going to do by parts off to the side. So when I integrate this, I'm going to have that negative e to the negative x. Now let's do by parts. So if I integrate x e to the negative x, I need to pick u, which is going to be x. So dv is e to the negative x. du is a derivative of u. V, I would need a negative 1 here, compensate with a negative out here when I integrate. So v is negative e to the negative x. By parts says when we integrate u dv, it's uv minus the integral v du. So it's going to be uv minus the integral of v du. So we have negative x e to the negative x minus. So if we think about our u substitution, u is negative x, and we have the negative. So when we integrate, we're going to get e to the negative x. So I'm going to put that in right here, minus negative x e to the negative x minus e to the negative x. So integrating those two pieces give me this. I'm going to take the limit of all of it after I plug in the limits 1 and b. So we're going to do some math here. Let's simplify this guy. So I have negative e to the negative x. I'm going to distribute that negative. So plus x e to the negative x plus e to the negative x. You can see how those are going to cancel. So now I'm taking the limit as b goes to infinity of x e to the negative x from 1 to b. So when I plug in the b, I'm going to have b e to the negative b minus 1 e to the negative 1. So I'm going to rewrite this. So there's b over e to the b minus 1 over e to the b. We want to know what happens as b goes to infinity. Oops. That's not e to the b. That's e to the 1. So the question is, what's happening to this guy as this goes to infinity? So let's pull that off to the side. We're going to take the limit as b goes to infinity of b over e to the b. So if we were to think about really large numbers, the top and the bottom are both going to infinity. So this is where we would use L'Hopital's. So let's take the limit as b goes to infinity, and we're going to take the derivative of the top, and we're going to take the derivative of the bottom. And we're taking that derivative with respect to that variable b. The derivative of b is 1. The derivative of e to the b with respect to b is just e to the b. And now you can see if we plug in infinity, that denominator is getting larger and larger and larger. So that whole fraction is shrinking. So when we come back over here, we're taking that limit. This guy is heading to 0. This is just the number. So my answer is going to be negative 1 over e. So this converges. So let's look at another one. Let's say we want to evaluate this. And we're going from negative infinity to infinity. So we're going to have to rewrite this. I'm rewriting this from negative infinity to 0. I'm thinking about this as e to the x squared. So I'm seeing the arctan come out already. And now I'm going to go from 0 to infinity. So let's talk about how we're going to integrate that. If I want to integrate e to the x over 1 plus e to the x squared. I'm thinking about a u substitution. U is e to the x. So du would be e to the x dx. So when we do our rewrite, this is our du. And this is 1 plus u squared. So you can see how this is going to be arctan of u, which for us would be arctan of e to the x. So we have the limit. I'm going to use a's and b's here since I have to think about limits as a's here, since I'm going to have two different variables. So a goes to negative infinity of a to 0 e to the x over 1 plus e to the x squared dx plus the limit. Now as b goes to infinity, replacing this upper limit there, that with a b, 0 to b, e to the x over 1 plus e to the x squared dx. So I'm taking the limit. And that's a goes to negative infinity. When I integrate this, I get arctan of e to the x from a to 0. And again, this is arctan of e to the x from 0 to b. So we're going to plug in our bounds limit as a goes to negative infinity. So this would be arctan. When I plug in 0, e to the 0 is 1 minus arctan of e to the a plus the limit as b goes to infinity. This would be arctan of e to the b minus arctan of e to the 0, which is 1. So let's figure out what arctan of 1 is. So arctan of 1. Anytime we're doing inverse trig, we're thinking about what angle is that. If I take the tangent of both sides, I would have this statement, 1 equals tangent of theta. So where is the tangent equal to 1 on the unit circle? Well, that's happening at pi over 4, where the x and the y coordinates are the same. So we know this guy is going to be pi over 4, and we know this guy is going to be pi over 4. Question is, what's happening to this and what's happening to this? So if I think about what's happening as A heads to negative infinity, so I'm going to do this off to the side here. Arctan of E, and I'm just going to use some notation that looks like this, negative infinity. Well, isn't this thing getting smaller and smaller? So isn't that approaching zero? Which means that arctan is approaching zero also. So we have pi over 4 minus 0 here. And we just have to think about what's happening here. Now, we already know that arctan of 1 is pi over 4. We want to know what's happening as b gets larger and larger and larger. Well, if you think back to your arctan function, looks like this. I'm taking the arctan of something that's getting bigger and bigger and bigger. That's going to approach that limit of pi over 2. Remember that pi over 2 was a horizontal asymptote for arctan, just like negative pi over 2 was. So we have pi over 4 plus pi over 2 minus pi over 4, which is pi over 4. And pi over 4 plus pi over 4 is pi over 2. So that was looking at integration over as we head towards infinity or negative infinity. We can also integrate over discontinuities using the same kind of idea. So let's say we have a continuous function that has a discontinuity. We're talking about infinite. So what that means is we've got a vertical asymptote here. At one of the endpoints, we could rewrite that endpoint in terms of a limit and apply the same process. It doesn't matter if it's a right endpoint, like it is in this case, or a left endpoint. We can even integrate if there's a discontinuity inside of the interval, but we're continuous on the endpoints. So let's say we want to integrate something like negative 2 to 2 of 1 over x. Well, we know that there's a discontinuity at 0, so we would rewrite it this way. And then we would replace the idea with this limit notation here. So that's what that third scenario is talking about. So let's look at just a couple of examples. Let's say we want to integrate from 0 to 1 dx over the cube root of x. So we know that there's a discontinuity at 0. So we're going to rewrite this. And I'm going to look at 0 from the right-hand side, because if I think about this graph, I'm looking at integrating to the right of 0. This thing is not continuous at 0, but I don't need to think about left and right hand in terms of limits. I need to think about just what's happening on this interval. So if you think about that number line, here's 0, here's 1. I'm really just concerned with what's going on in here. So I'm going to approach from that right-hand side. I can rewrite this as x to the negative 1/3. So when I integrate that, I'm going to add 1 to the exponent, divide by the new exponent. When I divide by 2/3, it's the same thing as multiplying by 3/2. And that's a b. We're going to have 3/2 times 1 to the 2/3 minus 3/2 times b to the 2/3. We want to know what's happening as b approaches 0. So this guy's going to go to 3/2 as b approaches 0. When we plug that 0 in, this is going to go to 0. So my final answer is going to be 3/2 here. Let's look at another example. Let's say we want to integrate from 0 to 2 dx over x cubed. Our discontinuity is again happening at 0. We're coming in at 0 from the right. I would rewrite this as x to the negative 3. So this would be x to the negative 2 over negative 2, evaluated from b to 2. I'm going to clean that up. That's negative 1 over 2x squared, evaluated from b to 2. So I'm going to have negative 1 over 2 times 2 squared, which is 4. So 2 times 4 is 8, minus negative 1 over 2b squared. I'm going to clean it up. So I have negative 1 over 8 plus 1 over 2b squared. I want to know what's happening as I approach 0 from the right. Well, that first limit is going to go to negative 1 over 8. But as I approach 0 from the right, you got to think about what that graph is doing. If I look at 1 over 2x squared, the graph, it's going to be a transformation of 1 over x squared. So it's going to look like that. As I approach 0 from the right, this thing's heading up to positive infinity, so that thing's going to diverge. So let's look at another one. If I look at the function 1 over x cubed, we have a discontinuity at 0, but they want us to evaluate from negative 1 to 2. So this is where we're going to have to split this, where the discontinuity is. So I'm rewriting this from negative 1 to 0, x to the negative 3 dx, plus 0 to 2, x to the negative 3 dx. Sorry about the dog barking. He must have heard something outside. So we're going to rewrite this in terms of limits. From thinking about that interval from negative 1 to 2, and 0 is where we have the discontinuity. This number line will help me figure out, am I looking at the limit from the left or from the right? From negative 1 to 0, you can see how we're approaching 0 from the left. And then this guy, I'll call it A. I'm looking at that interval now from 0 to 2. I'm approaching 0 from the right-hand side. This would be a to 2, x to the negative 3 dx. So now we're going to integrate. We x to the negative 2 over negative 2, and we need to evaluate from negative 1 to b. And for that next one, we're going to have x to the negative 2 over negative 2, evaluated from a to 2. So I'm going to use fundamental theorem of calculus, plug in my limits. So this is negative 1 over 2x. Let me rewrite it first. Over 2x squared from negative 1 to b, plus the limit as a goes to 0 from the right. Negative 1 over 2x squared from a to 2. So now let's do the fundamental theorem of calculus since I've rewritten. When I plug in the b, I have negative 1 over 2b squared minus negative 1 over 2, and then negative 1 squared is a positive 1. So that's just going to be a 2. Plus limit as a approaches 0 from the right. I'm going to plug in the 2, so negative 1 over 2 times 2 squared, which is going to be an 8. And then plug in the a, minus negative 1 over 2 times a squared. Now, let's clean all of this up just a little bit. So limit as b goes to 0 from the left of -1 over 2b squared plus 1/2 plus the limit as a goes to 0 from the right of -1 over 8 plus 1 over 2a squared. So I need to know what's happening as I approach 0 in both of these cases from the left and from the right. So again, I'm thinking about that function 1 over 2b squared or 2a squared, or I could think about it as 2x squared. That function looks like this. As I approach 0 from the left, it's diverging. This is heading to infinity. As I approach 0 from the right, this guy's heading to infinity. So this thing's just diverging. So we are not approaching a specific number there. We're heading off towards infinity.